This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers on the research paper, Probabilistic Mission Design in Neuro Symbolic Systems, which tackles the challenges of designing missions for unmanned aerial vehicles, UAVs, in complex dynamic environments. The authors propose a novel architecture, PROMES, to address these challenges. Let's start with the core problem. What are the key difficulties in designing safe and legal UAV missions, especially in advanced air mobility (AAM) scenarios?
The core problem lies in the inherent uncertainty and dynamism of human-inhabited spaces. UAVs must navigate environments with unpredictable obstacles, changing weather conditions, and complex legal regulations. Existing methods often struggle to integrate these diverse factors in a robust and interpretable way. Furthermore, mission design needs to be adaptable to different operator needs and regulatory frameworks.
The paper introduces PROMES as a solution. Can you elaborate on its architecture and how it addresses these challenges?
PROMIS uses a neuro-symbolic approach, combining the strengths of probabilistic logic programming with machine learning models. It integrates multiple data sources, including geospatial data, maps, sensor data from cameras, etc., and operator-defined constraints. These are encoded into hybrid probabilistic logic programs, HPLPs, which allow for reasoning under uncertainty. The system then generates probabilistic mission landscapes, PMLs, which represent the probability of mission success at each point in the UAV's state space.
The use of HPLPs is crucial. Can you explain their role in handling uncertainty and integrating different data types?
HPLPs are particularly well suited because they can handle both discrete and continuous probability distributions. This allows us to represent uncertain spatial relations, PRISM, the probability of an obstacle being present at a given location, and categorical information, today, whether a location is within a no-fly zone. The HPLP framework allows for a unified representation of all the relevant information, enabling probabilistic reasoning over the entire mission space.
The paper highlights the integration of machine learning models, specifically large language models, LLMs, and transformer-based vision models. How do these enhance PROMES capabilities?
LLMs allow for a more user-friendly interface. Operators can describe their mission requirements in natural language, and the LLM translates these into the formal logic required by PROMES. Transformer-based vision models, like the changeformer used in the paper, provide real-time perception capabilities. They can detect changes in the environment, e.g., new obstacles, and update the PML accordingly, making the system more robust to dynamic conditions.
The PMLs are a key output of PROMES. How are they generated and used for mission planning?
PMLs are generated by solving the HPLP, which incorporates all the constraints and uncertainties. Each point in the state space is assigned a probability representing the likelihood of satisfying all mission constraints at that point. This provides a probabilistic map of the feasible mission space, allowing for informed decision-making. The PML can be used for trajectory planning, risk assessment, and mission optimization.
The paper discusses the computational aspects of PROMES, particularly the challenges of generating high-resolution PMLs. What strategies are employed to address this?
Generating high-resolution PMLs can be computationally expensive. The paper addresses this through parallelization. Since the probability distributions at each point in the state space are independent, the inference task can be split into multiple subtasks and processed in parallel, significantly reducing the computation time. Furthermore, tiling strategies allow for distributing the workload across multiple computing devices.
The paper also explores the impact of resolution on accuracy. What are the trade-offs involved in choosing a suitable resolution?
There's a trade-off between accuracy and computational cost. Higher resolutions provide more detail but require more computation time. The paper shows that linear interpolation can be used to upscale lower resolution PMLs, reducing the computational burden while maintaining reasonable accuracy. The optimal resolution depends on the complexity of the environment and the specific mission requirements.
The integration of crowdsourced map data is another important aspect. How does PROMES handle the inherent uncertainties in such data?
Crowdsourced map data is often incomplete and inaccurate. PROMES addresses this by modeling the uncertainty in the map data using probabilistic spatial relations. The system generates multiple variations of the map based on the estimated error parameters, and then computes the parameters of the spatial relations from these variations. This allows for a more robust representation of the environment, accounting for the inherent uncertainties in the map data.
The experiment section demonstrates PROMES's application in various scenarios. Can you highlight some of the key findings?
The experiments demonstrate PROMES' ability to generate PMLs for diverse AAM scenarios, including urban environments, bay areas, and areas with rail networks. The results show that PROMES can effectively integrate multiple data sources and constraints to produce informative PMLs that guide mission planning. The experiments also highlight the effectiveness of parallelization and interpolation techniques in reducing computation time and maintaining accuracy.
What are the limitations of ProMaze and what are the potential avenues for future research?
One limitation is the computational cost of generating high-resolution PMLs, especially in dynamic environments where frequent updates are needed. Future research could focus on developing more efficient inference algorithms and adaptive sampling strategies. Another area for improvement is the handling of complex, long-range dependencies between different parts of the mission space. Finally, exploring more sophisticated methods for integrating diverse data sources and handling conflicting information would be beneficial.
The paper mentions the potential for integrating additional sensor modalities beyond vision. What other types of sensors could be incorporated and how would this enhance ProMIS?
Many sensor modalities could enhance ProMIS. For example, integrating LiDAR data could provide more precise 3D mapping, improving obstacle detection and avoidance. Incorporating weather sensors would allow for more accurate modeling of weather-related uncertainties. Furthermore, integrating communication data could help in modeling the availability of communication links and their reliability. The integration of these diverse sensor modalities would lead to a more comprehensive and robust representation of the environment, improving the accuracy and reliability of the PMLs.
The paper emphasizes the interpretability of ProMIS. How does this contribute to the safety and certification of AAM systems?
The interpretability of ProMIS is crucial for safety and certification. The use of declarative logic programs makes it easier to understand the reasoning behind the system's decisions. This transparency is essential for building trust in the system and for ensuring compliance with safety regulations. The ability to explain why a particular trajectory is deemed unsafe or why a mission is deemed unfeasible is crucial for debugging and for gaining insights into the system's behavior. This interpretability is a significant advantage over purely black box machine learning approaches.
Finally, what are the broader implications of ProMIS for the development of safe and efficient AAM systems?
ProMIS offers a powerful framework for designing safe and efficient AAM missions by integrating diverse data sources, handling uncertainties, and providing interpretable results. Its ability to adapt to different operator needs and regulatory frameworks makes it a promising tool for the development of robust and reliable AAM systems. The use of neuro-symbolic methods allows for a balance between the power of machine learning and the interpretability of symbolic reasoning, which is crucial for building trust and ensuring safety in this critical domain. The open source availability of ProMIS further facilitates its adoption and development by the wider research community.
The paper mentions the use of the method of moments for parameter estimation. Could you elaborate on the advantages and limitations of this approach in the context of ProMIS?
The method of moments is a relatively simple and computationally efficient technique for estimating the parameters of probability distributions. In ProMIS, it's used to estimate the parameters of spatial relations from uncertain map data. An advantage is its simplicity and computational efficiency, making it suitable for real-time applications. However, a limitation is that it may not be as accurate as more sophisticated methods, especially when dealing with complex distributions or limited data. The accuracy of the method of moments depends on the underlying assumptions about the distribution and the quality of the data. In ProMIS, the accuracy of the estimated parameters directly impacts the accuracy of the PMLs, so the choice of parameter estimation method is crucial.
The paper demonstrates the use of a changeformer for change detection. What are the advantages of using a transformer-based model for this task compared to traditional methods?
Transformer-based models, like the changeformer, offer several advantages over traditional methods for change detection. They excel at capturing long-range dependencies and global context in the images, which is crucial for identifying subtle changes that might be missed by local methods. Furthermore, transformers are less reliant on handcrafted features, making them more adaptable to different types of changes in image characteristics. The ability of the changeformer to operate on multiple scales also enhances its ability to detect changes at different levels of detail. However, transformer-based models can be computationally expensive, requiring significant resources for training and inference. The choice of model depends on the trade-off between accuracy and computational cost.
The paper mentions the use of linear interpolation for upscaling lower-resolution PMLs. What are the alternatives to linear interpolation, and what are their respective advantages and disadvantages?
Linear interpolation is a simple and computationally efficient method for upscaling PMLs. However, it can lead to artifacts and inaccuracies, especially in areas with sharp changes in probability. Alternatives include higher-order interpolation methods, e.g. cubic interpolation, or more sophisticated techniques like Kriging or Gaussian process regression. Higher-order methods can provide smoother and more accurate results but are computationally more expensive. Kriging and Gaussian process regression can handle more complex spatial dependencies but require more parameters to be estimated. The choice of upscaling method depends on the trade-off between accuracy, computational cost, and the specific characteristics of the PML.
The paper emphasizes the importance of interpretability for safety and certification. How can the interpretability of PROMES be further enhanced?
The interpretability of PROMIS can be further enhanced through several techniques. One approach is to develop more intuitive visualizations of the P&Ls, making it easier for operators to understand the system's reasoning. Another approach is to develop methods for explaining the system's decisions in a more natural language format, making it accessible to a wider audience. Furthermore, techniques from explainable AI, XAI, could be used to identify the most influential factors in the system's decisions, providing insights into the underlying reasoning process. These enhancements would improve the transparency and trustworthiness of PROMIS, making it more suitable for safety-critical applications.
The paper mentions the potential for adaptive sampling schemes. How could such schemes improve the efficiency of PROMIS?
Adaptive sampling schemes could significantly improve the efficiency of PROMIS by focusing computational resources on the most relevant areas of the state space. Instead of uniformly sampling the entire space, an adaptive scheme would prioritize areas with high uncertainty or areas that are likely to be critical for mission success. This could involve techniques like Bayesian optimization or reinforcement learning, which iteratively refine the sampling strategy based on the information gathered so far. Adaptive sampling could significantly reduce the computational cost while maintaining or even improving the accuracy of the PMLs.
The paper concludes by mentioning the need for advances in knowledge compilation and reasoning techniques. What specific advancements would be most beneficial to PROMES?
Advancements in knowledge compilation techniques would allow for more efficient representation and reasoning with HPLPs, reducing the computational cost of generating PMLs. This could involve developing more efficient algorithms for grounding and solving HPLPs, or exploring alternative knowledge representation formalisms that are better suited for probabilistic reasoning in large-scale domains. Advancements in incremental reasoning techniques would allow for more efficient updates to the PMLs in dynamic environments, reducing the latency between changes in the environment and updates to the mission plan. These advancements would make PROMES more scalable and responsive to real-time changes in the environment.
This has been a comprehensive discussion of the paper's key contributions and applications. Thank you.